video, I will present a solution to India EGMO TST 2022 problem 1. Firstly, we'll have a look at the statement. Let n be an integer greater than or equal to 3, and suppose positive real numbers x1, x2 up to xn satisfy that their sum is equal to 1. We want to prove that the following inequality is true. The sum of x1 to the power of 1 minus x2 plus x2 to the power of 1 minus x3 all the way up to xn to the power of 1 minus x1 is less than 2. This inequality might seem intimidating because we have positive real numbers as exponents. Now, exponentiation is really nicely defined for integers, but for real numbers not so much. But since this problem was stated in an Olympiad setup, we might be confident that there exists a solution that one can come up with. And actually, for inequalities of this type, where we have exponents that are positive real numbers, there are basically two tools to work with for proving them. The first one is weighted AMGM inequality, which is really strong, and there exists a solution to this problem using it. But we are going to solve this problem using Bernoulli's inequality. Bernoulli's inequality gives us a way to bound terms of the kind of 1 plus x to the power of r by a term like 1 plus rx. The inequality sign depends on the intervals which x and r lie in. Therefore, the Bernoulli inequality is not really one inequality, but a set of inequalities depending on different cases. But we are interested in very particular cases where -1 is less than x less than 0 and 0 is less than r is less than 1. That is because we know that xi to the power of 1 minus xi plus 1 is nothing but 1 plus -1 plus xi, all raised to the power of 1 minus xi plus 1. Furthermore, the xi are positive real numbers and their sum is 1. Therefore, they must all lie within the interval 0 to 1. Hence, -1 plus xi lies between -1 and 0, and 1 minus xi plus 1 lies between 0 and 1, which is the exact case I've written down right here. And for that case, we know that 1 plus x to the power of r is less than or equal to 1 plus rx by Bernoulli's inequality. Now, if this were an Olympiad problem and you would be in exam, it would be enough to state the name Bernoulli inequality and its statement, but I want to give some intuition for why this is true at least. Because we see that if we plug in 0 into this inequality, then we get something of the form 1 plus 0 to the power of r, which is nothing but 1. But this is also equal to 1 plus r times 0. Therefore, inequality is actually true at 0 and equality holds. Furthermore, we can also differentiate both sides. The derivative with respect to x of the left side is r times 1 plus x to the power of r minus 1, and the derivative of the right side is just r. We note that 1 plus x must lie between 0 and 1, and therefore is a small positive real number. And r minus 1 is a negative real number. Therefore, we are dividing r by a small positive real number raised to a positive value, if we view it like this. Therefore, this increases the value of the left side with respect to r, and therefore we get that r times 1 plus x raised with r minus 1 is greater than or equal to r. This tells us that for x less than 0, the derivative of the left side is larger than the derivative of the right side. But since we have equality at 0, this is basically enough to prove our inequality, and intuitively we can see this by drawing a diagram. 1 plus rx is just some line. This is the graph of 1 plus rx, where this is the point 0, 1. This tells us that the other graph of 1 plus x raised with r also goes through that point. But since it has a large derivative, if we look at x less than 0, it must come from below, which is why our inequality holds in this interval. Now we get back to our problem. What this inequality tells us is that xi to the power of 1 minus xi plus 1 is less than or equal to 1 plus negative 1 plus xi times 1 minus xi plus 1. But this is equal to xi plus 1 minus xi plus 1. At this point, we note that each summand from this sum can be bound with a term of this sort, which is really nice because we have those isolated xi and xi plus 1, but we already know that their sum is exactly equal to 1. Therefore, at this point, we can already plug this back in to our original sum and see what this gets us. We get x1 to the power of 1 minus x2 plus x2 to the power of 1 minus x3 and so on up to xn to the power of 1 minus x1. All of this is less than or equal to x1 plus x2 minus x1 x2 plus x2 plus x3 minus x2 x3 plus, and the last summand is x1n plus x1 minus xn x1. We note that each summand of the form xi is counted exactly twice. Therefore, all of this is equal to twice the sum from x1 up to xn minus all of the remaining product terms. We know that this inner sum is equal to 1 by what is given. Therefore, this is entirely equal to 2 minus the sum of x1, x2 plus x2, x3 up to xn, x1. And each of those is a positive real number. Therefore, we subtract 2 with some positive real number, which is always strictly less than 2. This is what we wanted to prove because we know that 2 is greater than our original sum, and therefore we are done.